question for tutorial sheet 5, not question 10. ME4111 engine mechanics. In this question here, we have something that looks a bit complicated, and again, it's a friction question. We're given the coefficient of static friction and dynamic friction for these rails here. That's keeping wheel placed by this cable. So it supports the hub there, and then we have this block A that is removed. So the tension is transferred to the cable, and friction is holding it all there. So we're told that the coefficient of friction changes from 0.5 down to 0.3, 0.4 down to 0.25. What happens? So what we'll do is we'll draw our free body diagram. So I take my sketch here, the cartoon that we have from the figure. Then I generate my free body diagram. And again, you can see that it's far from a work of art. So I have my representation of my system, which is just the wheel and the hub as one unit. So I have the outer wheel and then the hub. And then instead of any contact, I just show the forces. So with the tension T, this cable up here, we have the normal contact at this point here. So I'll just draw it in here so you can see that clearly. But there's, instead of the contact at the right there, there's a normal contact. And because the motion would be to go down the rails, we identify friction as moving up the slope. And then the other force I have is the weight. Okay, so essentially that's the forces that I have. This thing would ordinarily have a reaction force present there. It may also have a friction force, but it's taken away, so it's gone. Okay, so it's removed. There's no contact, therefore no forces there. Okay, so that's my free body diagram. I've put in some dimensions just to help me, because now what I'm going to do is I'm going to base my solution off this thing here, my free body diagram, rather than that. And you can see that what I've done is I've rotated my coordinate system just in line with friction force and reaction force. So X and Y there. So I'm going to break things, decompose this force and this force into their components. Okay, so there's a different color to show it. And again, this one. So I'll decompose T and NG. Right, so my solution. Again, I've left my free body diagram there just to give us a picture. So the sum of the forces in X equals 0. So I have F plus the X component of T and the X component of the weight vector. Okay, so F plus T cos theta minus NG sine 30 equals 0. And then the sum of the forces in Y, I have R the which is mg cos 30, and it's negative y direction, and then I have the component of t also, which is minus t sin 30. So again, it's come down in the negative direction, down that way. Okay, so we decompose like that. All right. So there are my two forces equations, and the next thing I'm going to do is I'm going to take moments about the point contact, which is I have ng, which I know, and then I can figure out what t is. So that's going to give me t of it. So minus t times 0.5 plus 0.25 cos theta. So that's the distance from the line of action of t to the point at which we're taking the moment. And then with ng times 0.25 sine 30, and again 0.25 sine 30 there is the distance. Okay, so we end up with t as being 85.6 newtons. Now with t determined, we can work back and calculate what F is. So we'll substitute that back in, we get F is equal to 171.1 newtons. So 171 newtons, just round it down. And we can also work out what the reaction force is. So that goes out to be 467.6 newtons. And the maximum friction force is 0.5 times that, so US times R. That gives us 233.8. So then I compare these two. And I can see that this friction, the value of friction required to hold this in place, this force here, needs to be 171 newtons. And the maximum force that can be produced there is 234 newtons. So therefore, equilibrium holds. My assumption of equilibrium is correct. And the value of friction is the value that is required. So it is this value, and it is acting in the direction as shown in the free body diagram. Now, if I go to change the coefficient of static friction to 0.3 and dynamic friction to 0.25, nothing else changes. I haven't changed the loading conditions. So now my maximum friction force becomes 0.3 times this. So it's 140.3. And I need 170 to hold it there. So now the system is going to be in motion, and we're going to have kinetic friction. So it becomes 0.25 times the maximum, or sorry, the reaction force. That gives me 117 newtons. And again, it is acting in the direction against the motion. Okay, so that concludes that question. It's a pretty convenient one. And that finishes to short sheet 5. So that's all our teaching content finished. My next step is going to be to work through some solutions to some past exam papers to give you a flavor for the kind of questions you will be facing in your assessment. So I think it will be next week, the latter half of next week, when I put up some solutions to that. If there are particular questions that you have that you'd like me to look at, or stuff you'd like me to go back over, please just touch base with me and let me know. Okay, thank you for listening.